Hey guys, welcome to day 13. Sorry the sound didn't work on the video I posted early this morning, but we're going to go ahead and try again. All right, so this idea of resonance. Sometimes when you go to draw a Lewis structure, there's more than one possible right answer. And resonance structures are kind of a way of showing that. So one thing you need to be aware of when you're doing resonance structures is you always need to count valence electrons. And typically speaking, you're going to end up with an even number. There are examples when they could be odd, but in most of our examples, I think they're going to be even. So with the first example, we're going to do nitrate. And we know that nitrogen gets 5 valence electrons. We know that oxygen gets 6 valence electrons. And if you notice there's a little negative symbol up here, that means that there is 1 additional electron. So add them all up, you get to 24 electrons. So when you go to draw the structure, sometimes it can be a little tricky to determine which atom goes in the middle. But for the examples I'm going to give you, we're at least going to show you where it is. So I'm going to start by counting the number of valence electrons, and there's lone pairs shown as dots, and then there's shared pairs shown as dashes. So you guys can kind of count along if you want. So for nitrate, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So every atom has an octet. We've got a grand total of 24 valence electrons. And what you're going to notice is that there is a double bond up top, and that oxygen only has 2 lone pairs, and that there's single bonds on the bottom, and those oxygens have 3 lone pairs. Generally speaking, we know that oxygen likes to form 2 bonds, but sometimes it can form 1 bonds, or even some cases it can form 3 bonds. But generally speaking, oxygen would prefer to form 2 bonds. But regardless, it's got its octet in all of our examples. So for the next example, I'm not going to count electrons for you, but it also has 24 valence electrons, and the difference is where you find this double bond. So in our first example, it was in the 12 o'clock position. In my second example, it's in about the 8 o'clock position. And in my final example, it's in about the 4 o'clock position. So all 3 examples have 24 valence electrons. All 3 examples have an octet for every atom. And the difference really is, where do we find that double bond? Realize that these electrons really don't belong to any 2 nitrogen and oxygen atoms, but they kind of belong to the whole molecule. Next chapter, we will explore this molecular orbital theory, the idea that electrons do belong to the whole molecule rather than to adjacent atoms. Okay. All right, so let's do some other examples. We just did nitrate. How about we do nitrite? So nitrate is 1 less oxygen, but we'll be able to do the structure nonetheless. Nitrogen gets 5. Oxygen gets 6 valence electrons each. And you guys notice that there is 1 additional electron. And when you add them all up, you get to 18. So if you count your electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. Every atom has this octet, and we have 18 valence electrons. And what you'll notice in this example is that they did kind of assign a negative value to one of those oxygens. That's kind of beyond the scope of this course, but sometimes you can kind of assign an atom a net negative charge. Just realize that nitrate is a polyatomic ion that does have a net -1 charge. Where you put that negative charge isn't super important right now. All right, so the only other possibility for nitrite would be that you could kind of flip the position of that double bond. In our first example, that double bond was on the right side, but in our next example, that double bond is on the left side. And in actuality, what you end up getting is you get a molecule in which doesn't have a single bond and a double bond, but rather it has kind of a hybrid, kind of a 1.5 bond all around. Just realize those 2 additional electrons don't really belong to any 2 atoms, but rather the entire polyatomic ion. All right, next examples. This is probably what I would assign you for homework, and the example is benzene. If you add up all the electrons, 6 carbons should get 24, and 6 hydrogens should get 6. So we should have 30 total electrons, and if you count, I'm sure you'll find 15 dashes, which represents. And really the only difference between these 2 resonance structures is where you place the double bond. And a lot of times when you're drawing benzene, you don't draw it as a carbon chain, but rather a hexagon with a circle in the middle. And the circle kind of indicates that there's this kind of racetrack around these 6 carbons where these additional electrons are being shared. So you can think of those carbon bonds as being alternating single and double bonds, or you can kind of think of it as a hybrid bond in which those additional electrons just kind of race around this 6 carbon ring. And benzene is a relatively stable structure, and it's quite common in chemistry. So next example would be dichlorobenzene, and dichloro means 2. And I'm not going to count electrons on this one, but I want you to realize that sometimes we alter the position of where these atoms are. So in my first example, we notice that these 2 chlorines are on adjacent carbon atoms. And they showed the benzene structure. Realize that each one of these carbons probably has a hydrogen sticking off of it. And if it has a chlorine, then I guess one of those hydrogens has been replaced. In this example, they've given it the name 1,2-dichlorobenzene. And if you were to start to number these atoms as you go around, I guess you would start there, number 1 and number 2. So 1,2-dichlorobenzene. And my next example, just realize not all the hydrogens have been shown, but they're there. This would be a 1, 2, 3, or a 1,3-dichlorobenzene. So those chlorines can be in adjacent atoms. They can alternate. They're 2 atoms apart. Or in the third example, they can be opposite. So if we're starting there, we might call this one 1-4-dichlorobenzene. So just realize that sometimes these chlorine atoms might adjust their position, and realize also with this, guys, they're not showing all the hydrogens. They're just kind of implied that they're there. Sometimes we cut corners in organic chemistry and we don't show all of our hydrogens, but we know that they are there. All right, guys, sorry that the video didn't come up. Let's do one more example and then we'll call it a day. So methyl isocyanate. If we kind of start by counting, carbon gets 4, hydrogen gets 1, but we have 3 of them. Nitrogen gets 5, carbon gets 4, and oxygen gets 6. And I think if we add all those up, we get to 22 electrons. Now, I'm not going to count for you guys, but all 3 of my examples have 22 valence electrons. Now, generally speaking, nitrogen would like to form 3 bonds. That's its most likely scenario. But in some cases, it can also form 2 bonds or even 1 bond. Hydrogen almost always, to my knowledge, forms 1 bond. Carbon, generally speaking, forms 4 bonds. In some cases, it can form 3. For my last example, oxygen generally forms 2 bonds, but most of the time it's going to form 2. Sometimes it can form 3. Sometimes it can form 1. So the box that I put around the number is the most likely number of bonds. And what you guys are going to notice is that in all 3 examples, every atom has an octet, and you can go back and count if you like. But what you're going to notice is the difference is the bonds between the nitrogen, the carbon, and the oxygen. We kind of have an alternating double bond, or a triple and a single. But regardless, all 3 of them do kind of follow this octet rule. It does kind of bend the rules as to how many bonds each atom can form. But regardless, in all 3 cases, every atom has an octet, or in the case of hydrogen, a duplet. Guys, sorry this video was late. If you have any questions, you can send me a private message. You can comment on Google Classroom, or you can look on the internet. I miss you guys. I love you guys. I'm giving you an extra day. I'll talk to you soon.